Similarity measures are at the heart of many data mining methodologies. For example, in predictive analytics, such as classification or prediction, we often want to find out how similar cases in the past performed. And in unsupervised data mining, such as cluster analysis, we need to identify cases that are similar to each other based on a number of variables, so that we can group them together. Therefore, similarity measures is an important topic to understand. Similarity measures gauge whether a group of observations are similar or dissimilar to one another. They are based on the physical distances between pairwise observations. A small distance between the observations implies a high degree of similarity, whereas a large distance implies a high degree of dissimilarity. Let's look at an example with three observations that have two variables, x1 and x2. The variables x1 and x2 can be any two numeric variables in the business problem. For example, they may be spending and age of a customer, or the cost and the price of a product. The three observations we have are observation 1 with the x1 value of 3 and x2 value of 4. Observation 2 with the x1 value of 4 and x2 value of 5. And observation 3 with the x1 value of 10 and x2 value of 1. Let's focus on the distance between observations 1 and 3 for now. What is the distance between the two observations? Well, the shortest distance between the two observations would be a straight line between the two observations. How can we measure this distance? If you recall from your geometry class, there is a theorem called the Pythagorean theorem, named after the Greek thinker Pythagoras, that would be useful in solving our problem. If we create a right triangle like this one, and call the three sides of the right triangle A, B, and C. And the line C is the shortest distance between observations 1 and 3. So the Pythagorean theorem states that A squared plus B squared equal to C squared in the right triangle. We can modify this equation a little bit and write it as the square root of A squared plus B squared equals to C. Now we have found the distance between observations 1 and 3. What we just described is a distance measure called Euclidean distance, which is the length of a straight line between two observations. It is also the shortest distance between the two observations, and it is commonly used for measuring distance or similarity between two observations with numeric variables. The example we just saw had two variables, but the concept can be extended to higher dimensional spaces with more than two variables. Here's the general formula for Euclidean distance between two observations with multiple numeric variables. It is essentially the square root of the sum of the squared differences between the two observations on all the variables. Using this formula, we can calculate the distance measures between any two observations. For example, the distances between observations 1 and 2, 1 and 3, and 2 and 3 are calculated here. Please try to calculate them yourself to see if you get the same answers as in the slide. Based on the distance measures, observation 1 and 2 are closest to each other because of the short Euclidean distance. Therefore, they are the most similar, and observations 1 and 3 are farthest from each other because the large Euclidean distance. Therefore, they are the most dissimilar. Another popular distance measure is called Manhattan distance, named after the city of Manhattan, which is laid out in square blocks. It measures the shortest distance between two observations if you are only allowed to move horizontally or vertically. Let's take a look at how we can find that distance between observations 1 and 3 if we can only travel horizontally or vertically, as in a city that is crowded with skyscrapers and traffic. There are two shortest routes to go from observation 1 to observation 3. First, we can go vertically down from observation 1, and then horizontally to the right to get to observation 3. Or we can go horizontally first and then go vertically to get to observation 3 from observation 1. But either way, the distances are the same. The horizontal distance that we traveled can be calculated as x1 for observation 1 minus x1 for observation 3. We would use the absolute value of the subtraction to ensure that the distance measure is positive. And the vertical distance that we traveled can be calculated as the absolute value of x2 for observation 1 minus x2 for observation 3. So the total distance is the sum of the horizontal distance and the vertical distance. The Manhattan distance can also be generalized to more than 2 dimensions. Here is the formula for Manhattan distance for multiple dimension spaces. Below are the calculations for Manhattan distance between our 3 observations. Please try to calculate them yourself to see if you get the same results. So why do we need various options for distance measures? Well, while the Euclidean distance is usually the default distance measure in a lot of the applications, it is more influenced by outliers or extreme values than Manhattan distance. Therefore, when there are outliers in the dataset, Manhattan distance measures may be more appropriate. Now let's look at another problem. Here we have 5 consumers, and we have data on their income and the number of hours they spend online each week. Let's measure the Euclidean distance between Jane and Kevin. So we apply the income and hours spent online for Jane and Kevin into our formula for Euclidean distance. If you do the calculation, you will find that the distance between Jane and Kevin based on their incomes and the number of hours spent online is 59,777. If you look at this number more closely, you will realize one problem. This number is almost exactly the same as the difference in income between Jane and Kevin, which means that the number of hours spent online played almost no role in calculating the Euclidean distance. Why is that the case? A closer look at the data will reveal that the income is measured in dollars, which is a much larger scale than the number of hours, which is measured in hours. Therefore, it tends to have much larger numbers. The formula for both Euclidean distance and Manhattan distance suggested that the variables measured using greater scales would have an oversized influence on the distance calculation. That does not sound fair, right? So how do we resolve this issue? To solve this problem, we can either standardize or normalize the data to make the observation unit-free before calculating the distance measures. To standardize the data refers to calculating the z-score, which is a unit-free measure of the number of standard deviations away from the mean. For example, to calculate the z-score for income, we need both the mean or the average income for the dataset and the standard deviation of the income for the dataset. We will subtract the average income from Jane's income and then divide the difference by the standard deviation of income. This provides us with a z-score of 1.2473, which means that Jane's income is 1.2473 standard deviations above the average income of the entire dataset. If the observation's income is below the average income, then the z-score would be a negative number, showing how many standard deviations the income is below the average. As you can see here, if we convert all values into z-scores, the data will no longer reflect the scale used to measure the variables anymore. Another common technique is to normalize the data, and the most popular normalization technique is the minimum-maximum normalization. To normalize the income value for Jane, we need the minimum income of the dataset and the maximum income of the dataset. We subtract the minimum income of the dataset from Jane's income and then divide the difference by the income range, which is calculated by subtracting the minimum income from the maximum income of the dataset. Since Jane has the highest income in the dataset of the 5 consumers, Jane's normalized income value is 1. For someone with the lowest income in the dataset, the normalized income would be 0. Therefore, the normalized value would always be a number that's between 0 and 1, thus not influenced by the scale used to measure the variable. This table shows the standardized and the normalized value for income and hours for all 5 consumers. Please calculate the Euclidean distance and the Manhattan distance between Jane and Kevin using the standardized values and the normalized values. Please verify if you get the same answers as the answers in the slide. Euclidean distance and Manhattan distance measures are suitable for numeric variables, but they are not suitable for categorical variables, such as the types of cars, the loan application status, or college admission decisions. However, in some cases, you may get away with converting categorical variables into dummy variables that have the possible values of 1 or 0, and then use the Euclidean distance or Manhattan distance measures without compromising the integrity of your analysis. What if you only have categorical variables in your dataset? How would you measure the similarity between these observations? Well, there are 2 primary techniques for these situations: matching coefficient and the Jaccard's coefficient. Let's first look at the matching coefficient. The matching coefficient is based on matching values to determine similarity among observations. The formula of matching coefficient is the number of variables with matching outcomes divided by the total number of variables. In other words, it measures the percentage or proportion of variables that have matching values between the 2 observations. Matching coefficient ranges from 0 to 1, and 0 being completely dissimilar and 1 being completely similar. Let's take a look at this example. In this example, we have 3 students and 4 categorical variables. Their majors, fields of study, sex, and whether they are on the dean's list or not. If you want to calculate the matching coefficient between student 1 and student 2, we'll first find the number of variables with matching values between the 2. There is only one variable that has matching values between the 2 students, which is the fact that both of them are on the dean's list. But they differ in terms of major, field of study, and sex. So the proportion of matching variables is 1 out of 4 total number of variables. Therefore, the matching coefficient is 1 over 4 or 0.25. As you can see, based on the matching coefficient, student 1 and 3 are the most similar because of the high matching coefficient, and student 2 and 3 are the most dissimilar because of the low matching coefficient. The other popular technique is the Jaccard's coefficient. Jaccard's coefficient works in a similar way as matching coefficient, in the sense that both use the proportion of matching variables as the similarity measure. But Jaccard's coefficient is more appropriate in situations where negative outcomes are not as important as positive outcomes. Therefore, it is often used when your variables are binary, especially when you indicate a positive or negative outcome, such as purchase or does not purchase, own or does not own, and etc. Let's consider this example. 2 consumers at a grocery store where thousands of products are available. If one consumer purchases only a Hostess cupcake, and the other purchases only organic apples, most people would conclude that these 2 consumers are not very similar to each other. However, a simple matching coefficient will account for the fact that neither of the customers purchased the thousands of other products that are available, and therefore erroneously produce a very high value of the matching coefficient. In this example, the fact that neither customers purchased the thousands of other products did not make them more similar, but the matching coefficient would tell you otherwise. Therefore, the formula for Jaccard's coefficient is dividing the number of variables with matching positive outcomes by the total number of variables subtracted by the number of variables with matching negative outcomes. Well, let's look at an example of how to apply Jaccard's coefficient to a problem. In this example, we have 4 online transactions where keyboards, memory cards, mice, USB drives, and headphones may have been purchased. The value yes indicates that the item is purchased in the transaction, and we consider it a positive outcome. And a no indicates otherwise, and we consider it a negative outcome. Between transaction 1 and 2, there are 2 matching variables with positive outcome: keyboard and the mouse. And 1 matching variable with negative outcome: USB drive. Therefore, the Jaccard's coefficient is calculated as 2 divided by 5, which is the total number of variables, minus 1, which is 2 over 4, or 0.5. Please go ahead and calculate the Jaccard's coefficients for other transactions yourself to see if you get the same results as those in the slide. Jaccard's coefficient also ranges from 0 to 1, with 0 being completely dissimilar and 1 being completely similar. So this is an overview of the important topic of similarity measures. To summarize, to measure similarity between numeric variables, we can use the Euclidean distance or Manhattan distance. To measure similarities between categorical variables, we can use the matching coefficient or the Jaccard's coefficient. When using the Euclidean and Manhattan distance, make sure to standardize or normalize the data in order to remove the influence of the measurement scale of the variables.